Okay, so in this video, we're going to be talking about some proofs using the formal limit theorem that we talked about in the last video. So just as a recap, the absolute value between x and a, the limit that we're trying to approach, has to be less than delta, a particular value, and that kind of implies that the absolute value of fx minus L on the y-axis has to be less than epsilon. And if you think about it for a second, epsilon and delta could be values that you could compute to be anything. So you could compute delta to be 0.0001, it could be 0.000001, it could go on and on, right? And for that particular value of delta, a corresponding value of epsilon would exist. So at this point in time, you need to understand this, that there has to be a relation between delta and epsilon, right? And we start with this side from in our proofs, right, and in the computation, and we eventually end up with an expression that's similar to this, right? And once we do that, we know exactly the relationship between epsilon and delta. And come to think of it, if you have that relationship, you could make that work for any particular value of delta and epsilon. So the concept of epsilon and delta tells you how close you can get to a limit, right? So this particular point, right, this particular point or number, it has to be less than something. If this is less than 0.1, then the distance between x and a has to be less than 0.1. This could be 0.0001. It could be as small as we want it to be, but it's never equal to 0. That's what you need to be sure of. And like at the same time, simultaneously, this distance between fx and epsilon, right? Basically fx and L has to turn out to be equal to epsilon, right? And epsilon has to be related to 0.0001 over here. It could be the same as we talked about in the previous video. उस केस में डेल्टा was turning out to be epsilon, which means कि इधर जितना 0.0001 का चेंज है उधर भी उतना ही चेंज आएगा. So the idea of this formal limit theorem is that we can make delta as small as we want it to be, right? But the idea is we do that for epsilon. We make it as small as we want it to be, and correspondingly delta can be as small as we want it to be. So using this relationship, we try to establish a theorem that talks about this. So in the first proof, we're basically going to talk about limit as x approaches a for the constant function, right? So we know for the constant function, which is basically fx equals c, right? The constant function has to be equal to c for all values of x, right? So regardless of the value of a over here, the constant function is going to give me c. So we need to prove this using the formal limit theorem. Let's try to do that. We know the limit over here, we know that f of x is actually c, if you think about it, as we've made sure over here in the diagram. So we start with fx minus L. Fx is c, and L is c as well, right? This has to be less than epsilon, right? So what this means basically is that epsilon has to be greater than c minus c. Or simply put, epsilon has to be greater than 0. When epsilon is greater than 0, what does that mean for delta? That's something we need to figure out. So what this basically means is that the value of epsilon has to be greater than 0, which we knew from the very beginning, right? But in this particular case, the value of epsilon has to be greater than 0. So if we were to talk about a over here and a corresponding like delta, right? The corresponding change over here turns out to be exactly L, right? So no matter what you do, you're going to end up at the same place. No matter what interval you take, the corresponding value of delta for that particular value would give me L, exactly L, which is exactly why epsilon has to be greater than 0. So regardless of the value of delta in this particular case, epsilon has to be greater than 0 because it ends up at the exact same point. So we're going to talk about another proof now, and in this proof, this is probably more important than this trivial situation over here. In this proof, we're going to talk about the limit of the sum of functions. So f plus g x has to be equal to L plus m. This is a rule we established in one of the earlier videos, and we need to prove it using the epsilon delta proof. Let's try and do that. So basically, for this, we need to first define the individual limits, right? So I'm going to say that when x approaches a, f of x equals L. We know that for a fact. And when x approaches a for g of x, that equals m, as it's shown over here. Can we use that to our advantage? Let's try. So for f of x, the formal limit theorem, when it is applied, is going to give us something similar to this. So f of x minus L. Actually, you know what? We're going to write the delta part first, so as to not confuse each other at this point. So that turns out to be x minus a. That has to be greater than 0. But since this is for f of x, there has to be a delta associated, like uniquely for x, right? Uniquely for f of x. So we're going to call it delta or f of f, right? Because they're two different functions, and the intervals of those two different functions can turn out to be different, right? So let's just consider that. And this would basically imply this, if you think about it for a second. F of x minus L has to be greater than 0 but less than epsilon. But since we know that we can change the value of epsilon according to what we want, right? We can change it and there would be a corresponding change in delta over here. So what we're going to do is, let's call it epsilon divided by 2, right? For our convenience. If you repeat the same process for delta of g, we get the exact same thing, but in this particular, we get g of x minus m, because now the limit is different. It's less than epsilon divided by 2. And once we do that, we will have a better idea of what's going on. So let's try to combine these two different functions. Now we're gonna add them up, right? But even before that, we need to find a new delta that corresponds to delta f and delta g, right? So this new delta has to be the same, because now since we're going to be referring to the sum of the two functions, the sum of the two functions is actually a new function. It's h equals f of x plus g of x, right? But what we're going to do is, we're not going to go into that detail. We're just going to make up a new delta, right? And this delta is going to be the minimum of both deltas. And this is not that hard to understand, right? Obviously, in this case, if the delta is 0.1 and that's 0.01, right, I'm going to go for the one that's smallest because I want that particular equation to be satisfied for both cases. So think about it for a second. If this is 0.01 and that's 0.1, if I choose 0.01 as delta, then that would automatically satisfy both these conditions. But if I choose 0.1, then this condition for g of x would be satisfied, but the condition for f of x wouldn't. But since we're considering two functions at the same time, we want both the conditions to be satisfied, both functions to be satisfied. So we're going to take the minimum of both deltas over here. And so now, basically, for the sum of the two functions, what we get over here is exactly this. The two functions being summed together, minus L plus M. So this is f of x, the new f of x. Let's call this capital F of x. And this is the new limit L prime. It's the same rule being applied in a recursive manner, but it's the exact same thing. That's what we need to understand. So if we try to simplify this, it's turning out to be fx plus g of x minus L minus M, right? And let's try to simplify that. We can group f of x with L, and we can group g of x with M. Both terms are now linked with their respective counterparts, as according to the equation that's mentioned, right? So let's just simplify this. We know that f of x minus L, and the absolute value of that turns out to be something, right? But what I need you guys to understand is this rule over here. This is known as the triangle inequality. It basically suggests that the absolute value of a plus b has to be less than or equal to absolute of value of a plus absolute value of b, right? So if we try to apply this over here, some courses by different instructors, they try to include the triangle inequality. It's something optional that you guys may choose to study if your specific instructor decides to teach you this. But we're just going to use this for this particular case. It's not that complicated to begin with. So this turns out to be f of x minus L, and that turns out to be absolute value of g of x minus M, right? And once we do that, we know exactly what this is. Since we're talking about an inequality, we can simply plug in fx minus L is less than epsilon over 2 over here, because we know that this has to be something, right? It has to be less than something. So we're going to put a less than equal to sign over here, and we're going to say that fx minus L is less than epsilon over 2. We can simply replace this, and we could put a plus sign over here, and then basically say g of x minus m is less than epsilon over 2, which we decided in the previous part. So what I'm basically just plugging in the inequality over here, because we can do that. We can exchange the roles of inequalities and equations, right? So if fx minus l is less than epsilon over 2 and g of x minus m is less than epsilon over 2, then this entire equation would be less than epsilon divided by 2 plus epsilon divided by 2, which gives me epsilon. So now that you think about it, we have this proof over here. This kind of proves that if we began with two functions f and g, right, we associated delta of f and delta of g with each of these functions. We tried to find the minimum of these deltas, and that minimum of all these deltas corresponded to the sum of the function over here. That turned out to be f plus g, and the limit turned out to be l plus m. And we tried to solve that, and as it turns out, we obtained a value of epsilon. Now you guys might be thinking, we chose a value of epsilon over 2, right? Why did we do that? Well, it doesn't really matter what we do. We did it in an attempt to further understand what's going on and to simplify the situation. Because if we chose epsilon over 4 and over here epsilon, then the term would turn out to be epsilon plus epsilon over 4. That turns out to be 5 epsilon over 4. This doesn't have any semantic meaning. Basically what this is saying is it's 1.25 times epsilon, right? Is that important? It's not really important. You know why? Because we can make epsilon to be as small as we want to. We choose to make it epsilon times 1, or basically epsilon, because it's convenient for us, right? So this was the lecture on the proofs of the formal limit theorem, right? So let's talk about a much more difficult example in the next video.